Anyway, so thank you for that extra time, Carolyn. To jump right in, the main purpose of the map that we prepared for the connecting ridge was to study the maximum usability as a field map. To that end, the next slide, please. To that end, we choose a map product scale of 1 to 27,000 if you print it out as a poster, but the actual digitization scale was 1 to 8,000. Next slide, please. The as I indicated, the main purpose was to investigate usability as a field map. So we also mapped boulders, which we weren't the first to map boulders in this area, neither manually nor aided by machine learning. Next slide, please. However, as has been discussed several times already during this session, there's some unique challenges here. We talked about the lack of real geologic contact, especially at this scale on the moon. So regolith texture becomes a main form of differentiating different surface units, and the compositional data that we have from MQQA, Clementine, and so forth is mostly unusable at this mapping scale. It can still inform unit interpretations, but we cannot use it for mapping at this scale, really. Then, of course, the elimination conditions, people have been complaining about that for several talks now. I know it's very challenging. That's why we decided not to use albedo or apparent albedo variations as a mapping parameter, because they're inherently difficult to differentiate from illumination artifacts, and you can easily get fooled. Nevertheless, there are several relevant line and point features, crater rims, slump scarps, and of course the aforementioned blocks or boulders. The crater rims at various stages of degradation, which is important to pertaining to as points of interest for exploration. The fresher, the more interesting. What we did not see whatsoever, and that's also detailed in the paper that came out last year, is there's no Shackleton or Tycho Ray signature within the mapping area. Because these features are broader scale features, or they're just off our mapping area. That's also why I got interested in Jeanette's map that she showed earlier, where she did see something around Shackleton at this scale. However, it's very fleeting, and we did not identify any signatures pertaining to Shackleton ejecta. If anything, it affects the entire mapping area more or less homogeneously with the data that we can judge it by. Next slide, please. I claim that the closest analog that we have that has been explored by humans so far is the Apollo 16 landing site, although there are some significant differences. So this is the scale-to-scale comparison. The 16 landing site was at 1 to 50,000 hours, at 1 to 27,000, so it's blown up a little bit to have the scale-to-scale. And you can see immediate differences here right away. Go to the next slide. The main takeaways here is that in the connecting ridge area, there's no distinct secondary clusters or ejecta units in a way that you can outline them nicely, as was done on the Apollo 16 map. Lineaments are visible in Stone Mountain and the adjacent massifs in the Apollo 16 area. Those are not there, or at least not at the scale as a mappable lineament in the connecting ridge area. Same goes for the distinct contact between the flatter areas, the low-lying valleys, as well to the adjacent massifs. It's much more gradual in the connecting ridge area. However, the connecting ridge area has distinct smooth crater floors with distinct, probably the only area where you can see some form of distinct contact to its surrounding, in the crater walls that it's residing in. Blocky knobs are all over the place, which are, interestingly, very absent from the Apollo 16 landing site area. At least looking at it on NAC images, I was not able to find a lot of blocks. There's almost none. Blocky knobs, I'm sorry for that. Blocky knobs, which is little block clusters. The I will we'll show an image of that later on. Boulder tracks are non-existent in either of those, at least none that we have been able to detect manually as well using machine learning. This is despite the fact that slopes reach 20 degrees in the area. And that's the slopes outside Shackleton crater. Yeah, and you know, with Shackleton crater, inside it's very steep, but even outside of it, on the connecting ridge, we easily get slopes of 20 degrees, and still there are no boulder tracks because there's just no source areas for it. Next slide, please. So the grade of degradation, just very quickly, how we define them from 1 to 6, basically. And we highlight the ones at class 6, which is the freshest, which also show distinct colors in the white color images, which we produced mosaics off of this area. And one distinct one I'm going to show in detail. If you move on 2 slides, please. There you go. So this is an example of the an example of a fresh crater, potentially the freshest crater pertaining to color wax signature, boulders around it, and morphologic freshness in the entire area. And based on that, that of course influenced our own traverse studies of the area, with boulders or blocks, as you like, around it being highlighted that we can safely identify multiple MAC images. Of course, there's always other potential boulders that you can make out in the halfway in the shadows and so forth, but those are the confirmed ones that are identifiable in multiple MAC images. I'll take the next slide. That's okay. This is something I mentioned earlier already in the chat. I highly suggest taking some inspiration from Arctic maps on the Earth when it comes to comparing morphologic and geologic maps. This discussion has been going on in the chat for a while. Morphologic / geomorphologic / geomorphic / geologic maps and so forth. At this scale, a geologic map on the moon is not feasible with remote sensing data, at least, and therefore we have to take some advice from the morphologic map of areas on the Earth, especially lacking vegetation, and compare them with geologic map the same areas, and we can learn a lot of things that work and don't work so well from these maps in terms of point and line features to be used, for example, here with the blocks, fur scarps, and so forth. That's just a general hint at the community to look at these kind of maps. Next slide, please. This is one of the blocking knobs I was referring to earlier, which are markedly absent from, for example, the Apollo 16 landing site, but here you find them all around Shackleton. There's no complete mapping of these all around Shackleton, by the way, so if someone has a student to let loose on that, that would be very interesting. Goransk et al. Identified these the first, as far as I'm aware, so I mapped them out here too, and these also influenced our traverse studies in the area, of course. They might be disintegrated ejecta blocks from Shackleton, therefore they might be very interesting in terms of disintegration, regular formation rates, and all that, and also tapping into actual lithology pertaining to Shackleton, and therefore also SBA and all that. The possibly closest thing to a reachable outcrop that we can get to. Next slide, please.
2 minutes.
And in order to reach it, you have to go to the far side facing slopes of the connecting ridge. That necessitates going there at a sun azimuth of 140 degrees west, shortly after the new moon, and of course we would need relay communication for that. Next slide, please. So this is one of those flat crater floors where you see something like a distinct contact to the surrounding inner crater wall. Next slide, please. That is in a very challenging area in terms of elimination. That's why it should be placed at the end of any traverse studies. Like this is like a high-risk area to go to unless you want to enter a PSR, but you get in very close one, and it's only illuminated over very certain stretches of time. Next slide. We differentiated different regolith textures as detailed in our paper. Safe to say, elephant high terrain should ring a bell. Next slide, please. That's the map as it is right now, downloadable as supplementary online material. Last slide, please. So, of course, it's not the last word. It's already sown. New mosaics are being produced. More block detections are possible. It's always iterative, but still, we need a single layer map product. I firmly believe in that. Thank you.